So welcome back, folks. I want to look at this question number 9 next, which is a good opportunity to practice interpreting the rate of change. Folks, when I talk about average rate of change in the context of slope, if that's not making sense, I do recommend that you go back and you take another look at the pre-work that was on the overview of slope. So let's go ahead and read this question here. We're told it costs Gabriella $40.95 to fill up her tank with gas with 12.6 gallons. And Gavin is able to top off his car's tank with about 3.2 gallons, and that costs $10.40. We're asked to give a linear function that models the cost of buying G gallons of gasoline. I want to talk about how we can interpret that instantaneous or that average rate of change and to build that model. So the first thing to realize is that I've given you the information that you need to think about independent versus dependent variables. So in this case, the G is the independent variable. And cost, C, is the dependent variable. So when we go to think about how our ordered pairs are going to look, our ordered pairs are going to have the form G for the cost of the gasoline, or for the number of gallons that we get, comma, C for the cost of that gasoline. So I've given you enough information here to construct two ordered pairs. The first ordered pair that we can construct is that the number of gallons for Gabriella was $12.6 gallons, and the cost of filling that tank was a cost of $40.95. If we were to construct the same ordered pair similar ordered pair for Gavin, Gavin put 3.2 gallons of gas into his tank, and it cost him $10.40. We're assuming here, I guess I didn't say this, we're assuming here that this is being purchased from the same pump on the same day. The price isn't changing in the middle of this scenario. So notice that we need to come up with a linear model. Well, our linear model is going to look like C of G is equal to AX plus B. And if that's not making sense, folks, that's again where I'm going to encourage you to go back to the pre-work to see that overview of slope where I introduced linear models. Okay. Oh, folks, I have a typo here. And this would be C of G, or A times G plus B. Okay. This is the model that we want to build. But notice that this A here is the same as slope, or the average rate of change. So let's go ahead and we're going to start building this linear model. We'll start off just using the variables x and y here, the way we might using the point slope form of the line that we talked about. So if I went ahead and use y1 and x1, we'll just know that I'm talking about the G and C of G coordinates here. So we can go ahead and build the slope of this line. And the slope of this line would be this 40, oops, that should have been red. Let's try that again. Would be this 40.95 minus 10.40. And we're going to divide that by the change in the x coordinates, or the independent coordinates. So 3.2, oops, sorry, that should be 12.6, folks. 12.6 minus 3.2. So if I were to go ahead and crunch this, I would end up with 3.25, and you could write that as a fraction if you wanted to, but I ended up 3.25 for that slope. If I were to go ahead and plug this information into my point slope form then, what I would end up with is y minus, and then I can pick either of these 2 points for the fixed point that I want to use. It doesn't matter. Even if I set up this slope formula a particular way, it doesn't matter which of these 2 fixed points I pick. So taking the first one, we would have y minus the 40.95, the y1 coordinate, and that is to be equal to the slope, which we just found to be 3.25. I'm going to go ahead and put the slope here in blue here just to help with the visuals. So we call that 3.25 times x minus x1. X minus, and then our x coordinate with the y coordinate of 40.95 was this 12.6. So folks, I am happy, if I ask you for the equation of a line, I'm happy with you giving it in this form. But we're trying to construct a linear model here, so let's go ahead and isolate the variable y. If I did so, I'd end up with y is equal to 3.25x. And then if you were to do this multiplication, what you'd find is that, and then add it over, you'll end up with 0 here. So our equation here is y is equal to 3.25x. Folks, just for familiarity, I used x and y here. I could have been using g and c of g through this whole problem. And the point that I want to make now is that we can give our linear function, c sub g, is equal to 3.25 times g plus 0, where I got, this was our slope from the model, I got that there, and then it turns out that the y-intercept was 0. Of course, you don't have to write the plus 0. I'm just emphasizing that because we said our linear model should look something like this. So we end up with 3.25g. Okay. If I were to go graph this function right here, the graph of this function would look something like this, where we've just shown that the slope of this line right here would be 3.25. So I think we've answered here part A. So let's go up and answer, well, we've kind of run out of room here. So this was the answer to part A, that c sub g is equal to 3.25g. Now, the next thing I want to talk about is how do we interpret this in terms of average rate of change? Okay. So one thing that I think is actually pretty interesting when we build these linear models with slopes is that if I were to go back and ask you what were the units up here in the numerator of the slope calculation, what were the units up there? Well, I've written that in red. Those red units corresponded to the costs, right? So the units up here would be dollars, would be the units, and we're dividing that by the units in the denominator. And the units in the denominator, those are in green, and those correspond to the number of gallons. So if we were to talk about the units on this 3.25, this would be $3.25 per gallon, which is a perfectly good way to write your answer. But what else could you do? You could go ahead and write your answer in the form that the slope was equal to 3.25 dollars per gallon. This is how mathematically we would write the units, but this is how in the real world you see those units shown up on a price tag. And so I think that's really interesting to get an opportunity to see that the average rate of change for this function here, which is always just this a value in our linear model, that average rate of change has a realistic interpretation. It's the cost of the gasoline in dollars per gallon. So that would be our answer to B. I'm sorry, I've run out of room here, folks. But for B, we would say that this is the cost of the gasoline in dollars per gallon. And the point that I wanted to emphasize here, my reason for doing this example, for various reasons, one was to practice building an equational line, like we've been doing, but the other one is to go ahead and show you where the units show up in this problem. And the units have a very real-world interpretation for that slope value in a way that maybe you hadn't thought of before. So folks, this finishes out our discussion. I'll make one last comment here at the end, and that is, and that comment is, I know that some of you may dislike this point slope formula line that you're learning now because you've learned another method that for the problems you were given, it was a better method. But I want you to know that going on in your math career, this point slope form of the line will be more important than the slope intercept form of the line. When you get into calculus and you're asked to find equations of tangent lines, this is the form you're going to want to know. And I often see my students in my Calc 1 class struggling because although they've seen this before, they don't have a lot of practice with it. And so it's my goal to give you that practice here in this pre-calculus course.